So to fix all my TOC work, ionic, positive, negative, or your metals are positive, your non-metals are negative. And if you're ionic, if you look down here, if ionic, you want to show the transfer of electrons, metal to non-metal, just like we did with Bohr diagrams, Mr. DeVries. Okay, so if you've got metal and non-metal, just like with the Bohr diagrams, you're still showing me the transfer. And then you're redrawing. What we did on the board when I was here on Wednesday, same idea, except we're doing them with easier diagrams. The covalent is the only one that's a little bit different. With the covalent ones, I actually had you guys drawing the overlap of the shells, which is wildly irritating, super convoluted. And it's the covalent ones that the Lewis diagrams are actually a lot better for. Remember, covalent is a negative and a negative, or a non-metal and a non-metal. The idea here is that both of the ions want access to those electrons. So the instructions here are similar to the Bohr diagrams for the ionic one. Draw the atoms, show the transfer, draw the ions in the brackets, step by step. If they're covalent, this is where things get more interesting. If they're covalent, show the sharing of electrons by circling the unpaired electrons. We did that in the first step when we were doing Bohr diagrams. I had you do Bohr diagrams, I had you circle the ones for covalent that were being shared. But then what you do, instead of drawing the overlap, you redraw the atoms with lines replacing each shared electron pair. So here's what this would look like for ionic. If I had lithium fluoride, LiF, a Bohr diagram for lithium, remember, Lewis diagram for lithium starts with the symbol of the atom and then just the valence electrons. Lithium's in the first column, it gets 1 right there. Fluorine is in the 17th, so it gets 1, 2, 3, 4, 5, 6, 7. This one is ionic. And because it's ionic, the metal is going to give, the non-metal is going to take. So this guy, this lone electron that lithium wants to give up, is going to join this space right here. And so now we redraw. There's the Lewis diagram for lithium. Valence shell is empty, positive. There's the fluorine. Everything is paired. It gained 1 electron, so it's got a charge of -1. The covalent is where it gets a little bit more interesting. So like O2, this is going to be covalent because oxygen's a non-metal, so oxygen bonded to itself is 2 non-metals. So you're going to have oxygen, 1, 2, 3, 4, 5, 6, and you're going to have oxygen, 1, 2, 3, 4, 5, 6. It has 6 because oxygen's in column 16 or group 16. So you can see here there's space. Each oxygen has space for 2. So these 2, actually it doesn't matter which 2, but 1 on one and 1 on the other need to be circled just like we were doing Bohr diagrams. And then maybe this one and that one, 1 on one and 1 on the other, need to be circled because those are the ones that are going to overlap to share. And then when you're actually drawing the Lewis diagram, you've got 1 oxygen, 1 oxygen. The first thing you should draw are those shared pairs. And it's going to be the shortest lines possible. So you're going to have one that goes straight across, another one that goes straight across. These 2 lines, each line represents a bubbled pair. So like where I circled this guy here, that's that line. Circled this guy here, that's that line. And then this oxygen on the left had a pair and a pair. So then that's where you're going to have a pair and a pair. And again, we talked about it with the Bohr diagrams. These guys, when you're looking at charged objects, the electrons are all negative. They're going to space themselves out. You're going to have something that looks like that. Questions about that? Okay. How many of you actually did the practice questions that I assigned related to this? Okay, a bunch of you. Okay, because I added 4 questions that I wanted you guys to do as well. No one did those? These extra ones? Okay. So I'll go through a bunch. Let's go through them. That's weird. Why would it say try also? Whatever. It's frustrating that TOCs are so incompetent. The first one would have looked like this. Magnesium and oxygen, ionic. There's magnesium, it's in column 2. There's oxygen, it's in column 3. I drew the transfer. There's the ion, there's the ion. Questions? Perfect. Okay. I'll show you this side first. I don't want you to see the other side. So I guess I can zoom in here to make this one easier to see. Let's make it less fuzzy. Okay, so 2 chlorines. Each one has 7. 1 pair shared. So 1 line in the middle. That's chlorine or Cl2. Questions? Well, chlorine. If you've got them, don't hesitate to ask them. Which one are you looking at, the chlorine or the BeF2? Okay. Because chlorine is a nonmetal, so they're going to share. If chlorine's a nonmetal, you got 2 of them. That's 2 nonmetals. It's covalent, so it's going to share that lone guy there and that lone guy there. They want to be partnered up. And so when you have a circled pair like that in a covalent bond, in the redraw, you draw it as a line shared between the 2 symbols, and that signifies that, and then you have the other lone pairs around the outside. Okay. So then the Lewis diagram looks like this. You've got it's the same as the Bohr diagram stuff we did on the board. When you've got the transfer, some of them are going to become negative, some of them are going to become positive, and you want to space them out so that they alternate the charge, whatever that is. We talked about this when we did Bohr diagrams on the board. So I've got 2 negatives and a positive, so I arrange them negative, positive, negative. That guy looks like that. The next one is water. When you've got more than 2 in a covalent, you need to make sure that you're grouping the right ones. If you group the 2 hydrogens together, then the oxygen gets left out. So 1 hydrogen needs to group with that oxygen, this hydrogen needs to group with that oxygen, and you get something that looks like that. If you drew it like this, if you said that and then you put a pair up here and a pair down there, I mean, I'm not going to get after you for it at this stage, but you're going to learn in the future that this is a better representation for how these things look. But really, you should have something that looks like one of those 2. Comments, questions, concerns from the Brooklyns? Gotcha. But you don't remember working them through? Okay. Okay, well, we'll spend some time practicing today. I'm going to get you to do more board work today. And then the 5th one should look like this. So the ionic ones, I think, are pretty easy. The ionic ones aren't the issue. The issue is the covalent ones. How do you share them properly, especially when you have more than 2 atoms? Because you guys are doing fine with the ionic ones on the board. You're doing pretty good with the covalent ones on the board too when we're doing Bohr diagrams. This version is supposed to be easier. Any questions about what's up there now? If you have them, please ask. Okay. Then the next chunk I wanted to do over the TOC was to use this booklet and also go through these 4. Did any of you attempt these 4 questions? Hands up if any of you did them. 1. Hands up if you attempted any of them. How many did you try? You tried one of them. Okay. Did she show you the answers to these ones? Did any of the TOCs show you the answers to these ones? No? Okay, cool. So, because only one of you actually did them, what I want you to do, just like Wednesday, I want you to hop up on the board, and I want you to try. Can you all read them? If I zoom out like this, can you see all 4 of these? Okay, this is a P, this is a B, and that's an R. So P is phosphorus, Br is bromine. Okay, and the bottom 2 are actually kind of interesting. What I'd like you to do is I'd like you to grab a partner or a group of 3, and I'd like you to move to the board and try these 4. You have lots of board space. If you need to come grab a pen, come grab a pen. Where's my key? My TFC is really that useless? He was here Friday, right? Yeah. Did he get swapped out at any point during the block?
You have to give a lesson next to his toe for the best to do.
Right, and then I had a TOC on Wednesday as well.
Okay. And all 4 of these, I will tell you now. If you got a group of 4, I want 2 groups of 2, not a group of 4. And you guys can do this. I'll push this guy back. This. 2 on one side, 2 on the other. I do not want a group of 4. 2s and 3s, that's it. They're all covalent. All 4 of these are covalent. Also got space on this front board here too. None of this needs to be. We got lots of space. But I want you to go through you go through the steps, draw them individually, show where they that's going to make it harder. I'll grab the classes. See what I can do. Yeah. Your name on the board? You're going to show light? You're cool light? Okay. How you doing? Yeah. So because each one of these guys has space for 1, this guy has space for 3, each one of these is going to share one of these. Yeah, you're good. Move on to the next one. You're good. Move on to the next one. what you've drawn here is actually straight lines. That's correct. You would redraw the velocity, just like that.
You do that.
Yes, except. Do you want this? Yeah. So your instinct was correct. N2H2 means somehow all four of those guys are together. So draw the H's as well. All four of them is work. You have to figure out a way to have those things shared so that everyone is fully shared. All of these are covalent, guys. There's no transfer of electrons in these. They're all sharing. You got to figure out a way to share them so that they're all full. You've already got these two shared, right? So hydrogen you have these two shared. Once you draw the lines, don't draw the dots here. So this one is done. This one is done. You're doing that. Then this one is almost done. But you still got an extra space here and two spaces on it. Scoop the rearrange differently so that both nitrogens have 8 around them. Each hydrogen is 2. Yeah, blank. That's correct. I mean, if we're going to get really technical, like if you take chemistry next year with Mr. Easton, in Chem 11, you'll see that the way you arrange them actually matters. This would just be a straight line right across the hydrogen.
You did the whole thing. I told you just do nitrogen.
But yes, that is the correct list item.
Wow, I just love right now.
Looks good up here, guys. Is this pen down here on the ground then?
Sorry.
That's great. Oh, wait a second. Yes, there's something not right. Oh. How you this is good. You have this. So those two go together, that's great. No, that should have been that one. That's great. Those two go together, that's great. That one has two, and these two go together. So you've got this pair is that one. This pair is that one. This one is that one. Where this drawing doesn't have share between these each line here represents one of these shared items. Because you have two of them. Why are the two here? Yes, but I've got students learning things, and you're going to the next class, and you're going to be extracting this class. Don't worry, I'm going back and covering things on Tuesday. Sorry. These guys were very clear on how to use the second. Yeah, it's not even the right ones. No. There's four of them. Are you making that's all four of them? Okay, go back to math. We'll deal with it in science. We'll deal with all the science in science. Go back to math. You can do it, I believe in you. Blank graphs. What? Are you working on physics now in the classroom? Use not one of the key. Whatever they say on my table. Okay, everyone come back. I love that you want to hear this. To work on your side inside. And go back. Yes. Those are separate things. Every capital letter is its own thing. So it's when you see capital and lowercase, that's where you have like a two letters that are each the capital or lowercase. Because this is capital, that's capital, you're gonna have carbons and hydrogens. Yeah, looks great. You're almost done. But they're not, like, they have to all be connected together. So you have one hydrogen connected to that nitrogen, one hydrogen connected to that nitrogen, but the nitrogen is not connected to that. Like, put it all together next to you need to hydrogen only has one. So you've got the right idea. You just swap those two. Hydrogen can have, because right now you use hydrogen as 4 electrons. If that's true. So the oxygen goes in the middle. Yep. Yep, that's great. Oh, no. Because remember, each one of those lines represents a shared pair of electrons. So that hydrogen there on the right has 4 electrons on it. Put it back where you had it for a second. The box. Okay. This hydrogen just have the one pair. This oxygen would have the 2 bonds hitting me. Carbon, yes. Carbon, if you remember, the original amount of carbon, carbon's in group 14, so it only has 4 on the outside. Oh, yeah. So, You need to connect them all four of these to one hole. Yep. The only thing I would do is just put that line right in there. You don't have to talk to your nose. Obviously, as long as in your head you're like, yeah, I can totally do all those, that's fine. I saw you do all of them, so I'm happy. There you are. Great. Almost not how we do it over here, guys. How are you two gentlemen? I know Sahib's been bouncing back and forth. Sahib, are these guys good? Sahib, are these two guys all good? Okay. Yeah, that's good. All right. Hey, over here, man. Okay. Where are you stuck? Yeah. Yeah, do that. And you can take care of these with the same way. Yeah. No, you're good. Yes. That is a CH4, yes. Oh, Corey, are you cool with everything that she's done? Okay. Because all of these are correct so far. Oh, one thing. You had one go here, one go over here. These nitrogens still have a pair there and a pair there. So you want to make sure that, so if you share these two, that's that line. But then you have another set to share as well. There should be a second line in the middle. To represent the fact that the nitrogen is sharing too. So you have one go over here, that's great. You have one go over here, that's perfect. And two here. Yeah, you can erase. Once you're done, I've checked them all, and I'm happy with what, and we're happy with what you've done. Do erase them, please. Someone doing the same thing with next block. Yeah, looks great. Almost. Yep. This is why you're supposed to draw all four of them, or all, in this case, 6 of them, and draw the sharing. Your miss, each carbon only has 6 electrons on it when you draw it. And it should have 8. Nope, because now they've got 2, 4, 6, 8, 10. No, now they got 5. Why? So now they got 8. Look how I did. Share 2 here. You share 2 here. Now there's alone and alone and alone and alone. That's why you draw them all. You did, except when you reach the oxygen, 1, 2, 3, 4, 5, 6. One of these got shared here. This one got shared here. These actually these two should be paired. Yeah, there. What happened? When one of them comes back, you can go. Okay. What are you guys doing up here? Yeah, and see that looks great. How do you feel about this stuff? Okay. Then try the last one. And I'll check out this one. Okay. Then we've got one more. That's a lot of red. I don't know, she's doodling. Yeah. Should be 2 carbons. If you do it that way, then the carbon's not being involved. Use an eraser, please, not your hand. Can I get you to erase yours? Just because I have another class coming in here doing the same thing next block, and I want to make sure that they are honestly good and not just looking at your guys' answers. Okay. Evelyn, that looks great. Are both of you comfortable with why that is? Both of you? Okay, you're good? Okay. Okay. Yes, you did. Looks great. No accepts. That looks great. Well done. Okay. So, that was the work I wanted. I don't remember what day it was. Akela, you can go. Okay. This page, I actually made a mistake in the book when I was photocopying these. At this stage, we are going to skip this page. And if my TOCs actually read you guys the notes that I leave them, what I want you to cover should be obvious. So my TOC yesterday did not do this with you. Lovely. Find this page. This is what I wanted them to do. We will go back to that energy stuff later. At the very end of the chapter, we'll come back to this. Okay, here we go. And this is a really big booklet, so let's do this. Okay, so names and formulas of compounds. You guys should have done a bunch of naming in grade 9. How many of you remember the naming in grade 9? Okay. Those of you who are interested in chemistry, who plan on taking chemistry in the future, this part's probably going to really irritate you because you do naming in grade 9, you do naming in grade 10, and you're going to start at grade 11, naming. The naming and formula writing gets done 3 times. I don't know why, but we do it again and again each time. So this first little bit here should be review. If you've forgotten it, that's okay. We'll go through it. So I got some names and dates. I'm not going to ask you to memorize names and dates. This is not a history class, but I think actually giving the history it gives it a little bit of context. I think it's kind of interesting. So 1919, this is 106 years ago. There was a conference of a group of chemists called the International Union of Pure and Applied Chemistry. Chemists from all over the world got together and they said, we all speak our own languages, but we need to find a way so that all of us can communicate the same stuff the same way. That International Union of Pure and Applied Chemistry got abbreviated as IUPAC. IUPAC, it's like Tupac, but with an I instead of a T. IUPAC. And this is an acronym that you'll see show up other places in chemistry. They'll say the IUPAC this and the IUPAC that. It came from this group of chemists that set down standards for chemistry. Like at this point, 106 years ago. Not that long ago, considering how long chemistry's been around. So they formed to establish convention and standards for the language of chemistry. They got together and said, this is how things need to be done. Especially how things are named, so that we can all call the same thing, and how they're expressed as chemical formulas. So again, for like the 3rd or 4th time today, ionic compounds are formed between metals and nonmetals. The reason it exists is because the compound is formed as an attraction between positive ions. Leave some space on that line because we're going to come back there in a second. And negative ions. And positive ions and negative ions aren't called positive and negative ions in chemistry. They're just not. We have another name for them. It's a shortened name. In chemistry, we call positive ions cations. Perhaps your Science 9 teacher taught you that. Perhaps they didn't. We call the positive ions cations and the negative ions anions. Sorry? Yeah. So I can't remember who it was, several years ago. Someone showed me a kind of an adorable way to remember this. Positive ions are called cations because positive and cats have paws. Did Mr. Gerbrand show it to you guys with a picture? And then the other one, there was no fancy way for the negative ions. It's just the other one is the anion. You got to remember that there's cations and anions. The positive ones are the cats. The negative ones are the ans. And then the naming rules for ionic compounds, relatively straightforward. You've seen this before. Which metal always comes first? Oh, I gave it away. The metal always comes first when you're naming these things. Whatever the metal is called is just what happens first. And the non-metal always gets listed second, and you change the name on the non-metal. The non-metal gets changed to IDE. And in an ionic compound, it doesn't matter how many of each atom there is present. Nothing changes. You don't need any weird other naming rules. Now, the ide, where the ide gets placed, it tends to be after the first syllable. So it takes some knowledge of remembering what syllables are in the English language. So like fluorine becomes fluoride. All right, here originally it was fluorine. It became fluoride. The first syllable there is the fluor, and then the ine becomes ide. Chlorine's the same, bromide's the same, iodide is the same. It was iodine or iodine, depending on where you are in the world. And then iodine becomes iodide. Oxygen's an interesting one because oxygen looks like this, oxygen. And then the question is, where do you put it? Does it go for the GEN? Does it change the EN to IDE? I've had students, when they first teach them this, like, yes, it's oxygide. It's not oxygide, it's oxide. The first syllable there is the O, the first letter. So then you replace, starting at the second syllable where that Y was, that's where it starts and changes to ide. So again, it takes remembering what syllables actually are. Sulfur becomes sulfide. Yeah. This one breaks that rule. A selenide is actually selenium. 4 syllables there, and it takes the last 2 out. But then nitrogen goes back to it. Nitrogen becomes nitride. It stops right there again. And then phosphorus becomes phosphide. I don't know why selenium is the way it is. Becomes selenide. I don't know. Maybe because selide sounds weird. But it's the one that kind of breaks the rule. So then, naming these things for simple ionic compounds like this, the naming is really straightforward. If I had magnesium and phosphorus, that thing would be called? Which one's the metal? Magnesium's the metal, which makes phosphorus the non-metal. The metal comes first, so this is going to be magnesium. And then phosphorus is going to become phosphide. If you're waiting for Roman numerals or something to show up, they're not yet. If you sort of remember things from way back in grade 9 and you're like, I know there's Roman numerals somewhere, we're not there yet. They will come, but not yet. So then calcium and chlorine, the metal there is calcium. So it's going to become calcium chloride. Calcium chloride. Sodium iodine is going to become, it'll be, the iodine becomes iodide. The sodium gets listed first, nothing changes there. Iodide. Aluminum becomes aluminum oxide, or aluminum and oxygen becomes aluminum oxide. Strontium and bromine becomes strontium. Again, the metal never changes. And the non-metal becomes bromide. This would have been the first naming bit you did at the end of, it's like the last thing you do in chemistry in grade 9. Is some of this naming stuff. Cool, we might actually end this well timed. Okay, next one. Those same ionic compounds. These are simple ionic compounds. Sometimes they're called binary ionic compounds. The formula of these things is relatively easy to do too. The formulas are the one I've been giving you already. Everything I had for you on the board today is a chemical formula. The PBr3s, the C2H4s, those things. So how those get written for these simple ionic ones, the photocopier cut off the word ionic there. When you have an ionic compound, the ionic charge, whatever it is important. It's necessary for grouping these things together. It's important for indicating how many of each ion is involved in the compound. We're back to the way it was.
My way.
Yeah.
And just don't send anything in yet until I give you the final go.
Okay, you had a conversation with this one or this one? And they understand? And what about the VSB portion of it?
We're just waiting to hear back from Jenny about
Okay, sounds good.
But it's going to be a go.
Sweet. Okay. So when two atoms react ionically, remember, reacting ionically, positive and a negative. They react so that the compound they form, and they just, because of the nature of physics now, with positives and negatives attracting and repelling, when a chemical compound comes together, they always come together to form a neutral. So the compound they form is always neutral, i.e., it has no charge. So all the positives, all the positives get together, all the negatives get together, and they sort themselves out, so that at the end of the day, all the positive charge and all the negative charge is balanced out. They're neutral. And they also react so that they have the least amount of each element necessary. It's like reducing the fraction. You could say 6/8, for example, but nobody says 6/8 because 6/8 is actual, except musicians, because 6/8 is actually what as a fraction? Close. Divide them both by 2. 6/8 is 3/4. Nobody says 6/8 unless you're a musician, because 3/4 is simplified. These things work the exact same way. So I'll show you the methodology here, and then I'm going to show you a shortcut. Again, this you should have done in grade 9. There we go. What compound forms between magnesium and chlorine? So when you're doing this, the big, full, long way to do this is you write down the elements separately, and it's not just the elements, it's just the element symbols. Always metal first, metal always comes first, with their charges. So now you're gonna have to start using your periodic table for all this, unless you happen to remember where they all are and what the charges all are. So if I want magnesium and chlorine to react together, I'm going to have Mg and I'm going to have Cl. At this stage, I don't know how many of each. The charge on magnesium is what? It's +2. And the charge on chlorine is -1. So remember, these guys need to react so that at the end of the day, there's as many negatives as positives, and you need the smallest amount of each. So the long way to do this is what I'll demonstrate here, and then I'll show you the shortcut. The long way is to say, okay, well, I've got Mg +2. Let's write it out again. I've got Cl -1. The mathy way to do this is to say, okay, you're looking at least common multiple stuff. If you're thinking about it through the math lens, what's the smallest number that 2 and 1 both go into? The least common multiple of 1 and 2 is 2. So I want to figure out what number I need so that my magnesiums are bringing +2 and that my chlorines are bringing -2. If magnesium is +2 already, I only need one of those. If my chlorine is -1, I need how many? 2. Because 2 times 1 is 2, -1 times 2 is -2. This is kind of the long, ugly way to think about it. Very good. So then at the end of the day, when you write the formula, to finish the formula, we do not write the charges in the final form. This thing would be MgCl2. And just like in math, if you have 1 of something, you don't write the 1. The fact that there is no little number 1 down here at the bottom means that I have 1 magnesium, that's it, and you put the little 2 down there on the Cl. I saw at the beginning you guys were writing them up high or big beside. We want to write them as subscripts down below. I'm not doing that because I'm being messy, I'm doing that on purpose. The IUPAC way to do this is to draw them dropped down. It's called a subscript. So like the opposite of an exponent. This would be the final form. You don't write the charge in the final form, and you don't include any 1s in the final form either. It's a 1. What do you mean? We're here? I'll show. I think I remember what you're talking about. I'm going to show you in a second. Dividing does show up here, but in the shortcut, not in this one. We're not dividing yet. If you think of these, depending on how your brain works, there's 2 ways to think about this, depending on how your brain prefers to work. You can either think of them as being least common multiples, in which case you're multiplying up, there's no division here. Or there's a backwards way to do it, which is this shortcut. This way requires, excuse me, less work, but instead of multiplying up, you're going to divide down. And here's what I mean. The shortcut is this. Sometimes this shortcut is called swapping and dropping. Again, first step, you want to write down the elements separately. The metal's always first. You want their charges. That first step is no different. Charge is still up in the top right. And then the shortcut for this, and the reason the shortcut works is it's because of how the least common multiples work. Often the way to find the least common multiple is just to multiply the two numbers together. 1 times 2 is 2, and so the least common multiple is 2. And so we can just swap and drop the charges. I'll show you what I mean. So the mg plus 2 and the cl minus 1 are here. A way to find the lowest common multiple is just to multiply those two numbers together. And you can see that, and in this case it works. The charge on the magnesium was plus 2, I needed 2, and the charge on the chlorine was minus 1, so I only needed 1 magnesium and 2 chlorines. So you can take that number there, we can swap the charges and drop them down because of the little quirk in the least common multiples. So this guy becomes MgCl2. And again, we don't write the charges once we've put the thing together, and we don't include any ones. So the 2 drops down there, the 1 drops down there, and then in the final form, we don't write it. So if I had another example, here, I'll draw a vertical line down here. I'll show you another example because we have time. The second example I'm going to show you is going to be, I'll make a box so I don't mess up there. I'm going to do magnesium and phosphorus. So that's just going to be magnesium phosphide. That's the name of the thing we're doing. And I'm going to show you both ways, the shortcut and the long way to do it. So if I've got Mg with a charge of plus 2, phosphorus is just the letter P, it's got a charge of minus 3. So if you're going to do it the long way, you'd say, okay, what's the smallest number that 2 and 3 both go into, or the least common multiple of 2 and 3? Six. And again, it's often the easiest way to find the least common multiple is just to multiply the two numbers together. So the smallest number they both go into is 6. The magnesium needs to bring positive 6. The phosphorus needs to bring negative 6. So the magnesium with the plus 2, positive 2 times 3 is going to give you that 6. And then negative 3 times 2 is going to give you that negative 6. So then this thing would just become Mg3P2. Which is the same thing you would have gotten if we swapped and dropped. Doesn't matter which way you approach it. Where things get a little bit dicey with this method is, let's say I did this guy here. Let's do another example over here. I've got calcium oxide. I'll do calcium oxide both ways. I've got calcium is Ca. What's the charge on calcium? Plus 2. I've got oxygen, which is O. Charge of what? Negative 2. So if we go back and look at doing it the first way I showed you, what's the smallest number that 2 and 2 go into? You sure? Is it 2 or is it 4? It's 2. 2 goes into itself. Yep. 2 goes into itself. So then I just need to bring, the calcium needs to bring plus 2. The oxygen needs to bring negative 2. How many of each do I need to bring positive 2 and negative 2? If each calcium is plus 2, how many calciums do I need to bring plus 2? I only need 1. Same thing with the oxygens. If I only need to bring negative 2 and each oxygen is bringing negative 2, I only need 1. So then this thing, is just going to be CaO. And that thing is electrically neutral. If you swap and drop, look what happens. And this is the danger of showing the shortcut. This becomes plus 2, that's minus 2. I see this all the time. If you swap and drop, yes, boom, boom. We do it without thinking about it. And you get Ca2O2. But I made a note right at the top of the page. It says they also react so they have the least amount of each element necessary. This isn't that. So then there is a step 3. If you're doing it this way, swapping and dropping, there's always a last step. And it goes back to the fractions example I gave you. Nobody says 6/8 because we simplify it or we reduce it. Same thing with swapping and dropping. If you can divide out, this is where we have to divide out. So can I divide 2 and 2 by anything? Yeah, 2 and 2 are both divisible by 2. So divide each of these by 2, pull out the common factor, and you'll get one of each. And we don't write the ones, it's just CAO again. You will never screw it up thinking about it this way. Least common multiples, unless you can't remember what the least common multiple is. If you say that the least common multiple of 2 and 2 is 4, it's a multiple, but it's not the smallest one. You always need to be able to pull out that smallest value. Questions, comments, concerns about this stuff? Okay, is it coming back from grade 9 slowly? Okay, this is it. I'm not doing anything more than this today. What I'd like you to do, here's your homework. There's 8 questions. You can get, and there's 10 minutes and there's 8 questions. You can absolutely get this done and then have no homework. I want you to do that. Multi up above, that's your homework. These 8 questions, that's it. We will review multivalent metals tomorrow. This is where the Roman numerals come in. Crank out those 8, and then you can pack up. Okay. Tomorrow we'll do multivalent and, oh, we have a short block tomorrow. Yeah, we'll still be fine. Multivalent and polyatomic. No, it's next week. Tomorrow's Abby's Got Talent. We do 6 minutes on each block. Aren't you in leadership? Are you in leadership? Sorry? Yeah, but to lengthen lunch, to make the talent show fit, they took 6 minutes off each block. They didn't tell you that? I guess they didn't tell you that. Meet the teachers next week. Wednesday, Thursday next week. Yeah, a lot.